So in Chapter 20, we're going to look at geometric thinking and geometric concepts. So broadly defined, geometry is a network of concepts and ways of reasoning used to explore and analyze shape and space. For too long, geometry curricula emphasized the learning of terminology. But geometry is much more than vocabulary and naming shapes. I actually had a really good geometry teacher in high school, and we focused a lot on generating proofs, and it was very foundational for me, and I felt like I had a great understanding of what geometry was. But I think early on, it's focused so much on terminology that students don't have a good spatial sense of what geometry really means. First, it involves developing spatial sense. Spatial sense is an intuition about shapes and the relationships between them. And in our previous PowerPoint on measurement, students start to understand this when you let them explore those volume formulas, like the relationship between the volume of a pyramid and a cylinder, or a cone and a cylinder as well. Those are really foundational exercises that help to develop spatial sense. Spatial sense includes familiarity with geometric descriptions of objects and position, and the ability to mentally visualize objects and have an appreciation of geometric forms in art, nature, and architecture. In addition to spatial sense, geometry has a number of significant content goals that apply to all the grade levels. 4 of these are shapes and properties in 2 and 3 dimensions, transformations, which include a study of reflections, rotations, and translations, as well as the study of symmetry and similarity. The third skill is location, which basically refers to coordinate geometry on the XY plane. And the fourth one is visualization of objects in the environment and the ability to draw and recognize objects from different viewpoints. And we're going to look at achieving some of these goals throughout today's PowerPoint. All learners are capable of growing and developing the ability to think and reason in geometric contexts, but this ability requires ongoing and significant experiences across a developmental progression. In geometry, the reasoning or learning trajectory that learners follow is best modeled by the Van Hille model. The Van Hille model is named after 2 Dutch researchers who were husband and wife. The Van Hille model has influenced geometry curricula worldwide and can really help teachers understand developmentally appropriate next steps for their students' geometry instruction. The Van Hille model is a 5-level hierarchy of understanding spatial ideas, and it's on your screen here. Let me explain a little bit how this model works. The levels are developmental. Learners are going to begin at level 0 and progress to the next level through experiences with geometric ideas. You see an overlap between these different levels. Why? Well, each level has an object and a product of thought. So in the visualization stage, which is the first one, your object is shapes, the product of thought is classes of shape. But then you see an overlap with step 2, the analysis stage. Well, the previous level's product becomes the next level's object. So they produce this level or product of thought. That's going to be the object that they work with to produce in the next stage. So in the analysis phase, classes of shapes is the object. The product of thought is properties of shapes. Properties of shapes becomes the object in the informal deduction phase, and the relationships between these properties becomes the product, and so forth. You see how each stage then proceeds. This model leads us to some key characteristics that we're going to review in the next slide. I know I mentioned in the previous slide that the Van Hille model of geometric thinking is developmental, where each stage is dependent upon the previous one, but there's some other key characteristics too, and some of them I know are blatant. It's sequential. To arrive at any level above 0, the student has to move through all the prior levels. The products of thought at each level are the same as the objects of thought at the next level, as we discussed in the previous slide. When we talk about it being developmental, what we really mean is when instruction or language is at a level higher than what a student is at, the students are going to be really challenged to understand the concept that is being developed. And what they might revert to is simply memorizing a relationship without really mentally constructing it and understanding it. So it's really important for you to be in tune to where each student is at developmentally so you can help them gain a full understanding of properties. What's quite interesting is the developmental of geometric thinking is totally age dependent. A third grader or a high school student could be at level 0 if they have not been properly scaffolded and moved through the system developmentally and sequentially. It's also experience dependent. You notice throughout this entire course we talk about giving students opportunities to experience the math, to create it, to do it. Well, that is absolutely necessary in geometry. Advancement through the levels requires geometric experiences. Students need to explore, talk about, and interact with the content at each level while increasing their experiences to move on to the next level. We're going to take some time and look at each level in the Van Huyl model a little bit more in detail. The first stage is visualization. In this stage, students recognize and name figures based on visual characteristics, and in doing so, they begin to sort and classify shapes based on their appearance and distinguish them as alike or different. And that's all based on different criteria. Perhaps they would put triangles all together because they realize they have 3 sides, and put quadrilaterals, squares, rectangles, parallelograms into a category because they have 4 sides. Maybe they put ovals and circles into a category because they're smooth. There could be so many different ways that the students classify, but in the visualization category, this is when they are doing so and based upon the visual differences that they perceive. So in level 1, students start to analyze the shapes, and they do so by looking more intently at shapes within an entire class. So they're able to sort in greater detail and describe all the properties, maybe of rectangles, of squares, of parallelograms, of rhombi, of rectangles. They really focus on the properties that make a certain shape that shape. And they start to realize that if a shape belongs to a particular class, it has all the corresponding properties of that class. So if it's a square, all the sides are equal and all of the angles are right angles. The next stage in the Van Huyl model is level 2, which is informal deduction. And there are a couple key traits that I really want to emphasize. There are 5 that are on here, but the first 2 are the most pivotal. In this stage, students are able to think about the properties of geometric objects without focusing on one particular object. And they can visualize it without seeing anything and enumerate those different properties. They're also able to engage in if-then thinking. Like for instance, maybe they're thinking or they're asked, if all 4 angles are right angles, then what shape is it? Well, they might deduce then it has to be a rectangle. And they can classify shapes with a minimum set of defining characteristics, so they are able to determine what are the key criteria for a shape to be this specific shape. And even though I said that the first 2 properties are most critical, it really is that third one, that they can classify shapes within a minimum set of defining characteristics. That really is a hallmark of this stage of thinking. Okay, so let's move on to the next level. Level 3 is deduction. In this stage, students analyze informal arguments, and they're able to work with abstract statements about geometric properties and make conclusions based on logic, like why do diagonals of a rectangle bisect? One thing I really do want to stress about the previous levels is that precision with shape properties is absolutely 100% critical. Sometimes you may notice that worksheets are designed in a faulty fashion when it comes to geometry at the 0 and 1 level, insofar as they're not precise. And precision is critical for these properties to actually make sense. To get a better idea at what I'm talking about and the lack of precision in some of the early elementary worksheets, pause this and watch the YouTube video that I have attached here. It's a great example of how geometry is about precision and how important that is. You'll notice that I've devoted one slide to both levels 3 and 4 because they're a little bit beyond the scope of this book and at the upper levels once you're out of elementary school and even into college. So level 3 is deduction, and that's where students are working with proofs, and that's going to be your 8th grade to early high school geometry. And level 4 is rigor. That involves the whole axiomatic system, and it's the level that math majors study in college. And again, it's just beyond the scope of this class. So what are the implications for instruction based on the Van Huyl sequential model? Well, for you, you're really going to be looking at scaffolding and helping students move from level 0 to 1 and then level 1 to 2. And you really do need to be aware that the collection of geometric experiences that you provide your students are the most important factor in helping them to move up that developmental ladder. And there are specific strategies that you should employ to help your students move from one level to the next. So for instance, moving from level 0 to 1, you really want to stress and focus on the properties of the figures rather than just simple, quick identification. You want to challenge your students to test ideas about shapes using a variety of examples from a particular category, and you want to give them plenty of opportunities to draw, build, make, and put together and take apart shapes in both 2 and 3 dimensions. What about moving from level 1 to 2? You definitely want to challenge students to explore and test examples. Help them to make and test hypotheses based on the minimal number of criteria to be a certain shape, making sure that it fits all the sufficient conditions. And actually encourage them to attempt informal proofs and to use informal deduction by using keywords like all squares are rectangles, but only some rectangles are squares, and using keywords such as that so that they can start to use some informal deduction. Here's a great activity to help students move from level 0 to 1. This activity particularly focuses on sorting and classifying shapes, which ties together both of these levels. This activity, which is 20.5 in your text, is called What's My Shape? What you want to do is you want to first cut out a bunch of 2D shapes on cardstock, and you're going to do a double set of them. And you're going to glue one set of the shapes in folders, like file folders, that are your secret shape folders. And then the other set you're just going to put out on a desk or table as reference for the students. You're going to designate one student as the leader, and they'll hold the secret shape folder. The other students will have to ask yes or no questions to find out the shape that matches the shape in the folder. And as the group eliminates shapes, they can turn them over or discard them that are on the reference table. They cannot ask the question, is this the one? They have to ask questions that relate to the shape properties. So this is a great way for them to start linking those key characteristics and precision to the shapes of and the shape properties. And you could do multiple shapes. You could do triangles and different quadrilaterals, or you could focus just on one set, like all quadrilaterals. But it's a great opportunity for students to work on moving from level 0 to level 1. Students need to freely explore how shapes fit together to form larger shapes. This is known as composition, and also how larger shapes can be made of smaller shapes. This is known as decomposition. This supports students' understanding of area, surface area, and volume, and they're great objects for helping students to do this. Look at the slide. You could use tangram puzzles, and they can use shapes to put together a full-size outline and learn how to manipulate them. There's the mosaic puzzle, and the mosaic puzzle is great because the set contains 5 different angles, so it can lead to discussions about different angle groupings like right, acute, obtuse. And there's a mosaic puzzle worksheet that you can access in your ebook in this chapter. Geoboards are also awesome, and you could buy cheaply a small set of these for your class, but you also don't have to have the actual geoboard. You can use geoboard printouts that are just like what you see at the lower right of your slide here, and it's just small little collections of printed out geoboards so the students can draw on them instead. And you can print out ample amount of these, and students can record on there, and it gives them the same feel as working with an actual geoboard. And these are great for constructing two-dimensional shapes with rubber bands or by pencil. The table on this slide lists some important categories of two-dimensional shapes. Quadrilaterals have several subsets, and students are going to have to work through identifying what these subsets are and which ones belong to multiple categories. So, for instance, parallelograms consist of rhombi, squares, and rectangles. And squares really are everything. They're rhombi, rectangles, parallelograms, and trapezoids. And students need to be able to know what direction these relationships go. That all parallelograms are trapezoids, but not all trapezoids are parallelograms. If you draw an ellipse or set of ellipses like what is at the bottom right of this slide, that's really helpful in helping students reason through the properties and which sets are subsets of the other sets. In addition, there are plenty of other properties that are really important. You want the students to come to an understanding of concave versus convex. Concave, a very simple way to initially describe it, is it's like a dent in the shape. It really means that you're going to have an internal angle that's greater than 180 degrees, but visually it looks like a dent. Convex would not have a dent. With triangles, you want students to be able to discriminate equilateral, isosceles, and scalene. Those are different relationships with the side lengths, and then acute, right, and obtuse are different relationships with your angle measurements. And then, of course, making sure they have that solid understanding of all the subsets of the quadrilaterals. These are all part of the Common Core State Standards of Math that your students are going to need to be familiar with by 5th grade. Important and interesting shapes and relationships also exist in 3 dimensions. And this book, interestingly enough, classifies prisms under cylinders, which you may not be used to because you may have been taught that cylinders refer to prisms with only circular bases, but in actuality, cylinders do include all prisms. So this might be a new concept for you to adjust to. But it's actually better that they're grouping the prisms under the cylinders because broader categories help students focus more deeply on the properties that make the shape what it is, not just what it looks like. So there's thinking more about the actual properties, that I have these 2 parallel bases that are connected by another rectangular solid. What I would like you to do is to pause this, read through these different properties, especially how we can sort these shapes by faces and surfaces and what properties relate to each of the different shapes. And look at also the sorted groups as well visually so that you can see what makes something a cone versus what makes something a pyramid versus what makes something not a cone, and make sure that that's all clear to you. This activity provides a good way to introduce a category of shapes. And in fact, there is an initial master handout that looks just like the graphic that's on your slide. And then from there, you can create several other systems of 3, those shapes that have something in common, those that have none of the that property in common, and then those that the students have to select that do have the same property in common. You can create several of these, but it's nice to have a baseline to work with. And I believe that it's right in activity 20.10 in your e-text, which is entitled Mystery Definition, that you can click on the link to access the initial master handout. But what I like about this is it really is a puzzle, and it allows students to develop the concept of definitions in their own way. So what you do first is you present students with a series of shapes and you say all of these have something in common. And then in the second step you say, well, none of these have it. So the students have to discern between the 2. What are the differences between those shapes that all have something in common and those that do not? And then in the last category they have to select all of those shapes that also have that same property in common. Students might wrestle and struggle with this a little bit, and they might need hints, and you might have to help them hone in on things such as angle size or side lengths, congruency. And again, what is really nice about this activity, its greatest strength, is that it allows students to develop ideas and informal definitions based on their own concept development, so it gives them ownership. We're going to look at this activity 20.15 more in class, but I wanted to provide it here in the PowerPoint so you could take a minute and look at it a little bit more in detail. But it really gives students the ability to start working with conjectures and developing proofs. And I think it's so important that you start introducing students to this in the elementary, middle school years, so that geometry just isn't this segregated brand new concept that they come to and are immersed in high school, because it's a huge item that they're going to encounter in the real world. Especially, we have so many students that end up going into engineering, and they need to have their feet strongly and firmly planted in geometry. And in addition, it's one of the biggest sections on both the ACT and the SAT, so we've got to prepare students more so for geometry, and we need to start giving them experiences early on. But giving them some little bits of experience with proofs early on too will help them when they get to geometry not feeling like the idea of a proof is something so foreign. So maybe take some time and read about this activity on page 506. This slide is a continuation of the activity on the previous slide, and it just simply shows the logical reasoning that it encourages. So you could pause this and just read through a hypothetical student reasoning that is produced from this activity, and why that would be good in terms of developing students' higher order reasoning skills. In addition to the previous activity, we're going to explore the Pythagorean theorem in class as well. This really should be, according to the Common Core State Standards, explored in depth in 8th grade. But to be honest, I don't know that it is. From my experiences with different 8th grade students, I think that teachers are just counting on it to be something that's covered once students get into high school. But I think this puts students at a disadvantage. It really needs to be something that students encounter when they're in 8th grade. And really, for it to make sense and for students to have an appreciation of the Pythagorean theorem, they need to investigate it in depth. And it's not a very difficult proof for them to wrap their mind around at all. And there are several different ways that it can be proved or illustrated, and that's what we're going to look at in class or a geometry lab. But if you want to take some time and begin to explore it, you could actually look at the visual that's on your screen on the right. And what it shows you, it says the two large squares together are a proof without words. Can you supply the words? So maybe think through if there is a way that you can think through that. It's a good kind of stimulation and thought provoker before we actually do so in class on Tuesday. Transformations are changes in position or size of a shape and are a major focus of 8th grade in the Common Core State Standards of Math. But this begins much earlier with the study of symmetry in 4th grade, and mirrors are a great hands-on tool for investigating symmetry. Symmetry is extended in the transformation of reflection, so that's why symmetry is related to transformations, because it's reflection. Movements that do not change the size or shape of the object are called rigid motions. That's what differentiates them from dilations, which changes the size of an object. Reflections, translations, and rotations are rigid motions that result in congruent shapes. And they're all different ways that you could demonstrate and let your students have opportunities with this. Mirrors are one, but you can also use geoboards and have students reflect and rotate, and so they can see and also translate to a specific spot, and they can see how the shape changes, both its direction and its position. There is a great tool on the Illuminations website that allows students to virtually engage in all of these different transformations, and I think you should take some time and test it out. It's so good to have these e-tools available, and in the classrooms that you're going to end up being in, students are going to have access to iPads, or perhaps they will all have a laptop in their classroom. So you're going to have greater ease with allowing students to explore these tools. In addition, plenty of you will probably end up teaching online, so students will have instant and immediate access to these tools. So take some time, look at the Illuminations website. What I love about this is because it's through the National Council of Teachers of Mathematics, you can be assured that they're going to constantly update this. This is going to be something that you're going to have access to. It's not going to become irrelevant or something that is not maintained. So having greater familiarity with the tool and what it has available for you as a teacher is going to be such a great resource once you're out in the classroom. I've always had an affinity for music and art, and I love to see the connection between mathematics and different art forms. And one way that you can allow students to start to see that interdisciplinary connection is through tessellations. Tessellations are a motivating artistic application of transformation. They're simply repeating geometric patterns. And if you've had an opportunity to do any historical research on tessellations, you'll see that the master of mathematical artwork and employing tessellations is M.C. Escher. And he has such a cool biography. What's so neat about him is that he did so poorly in school, and he didn't even realize that he was gifted in any capacity at all other than with art, that he had no idea that he had good mathematical intuition until he started to develop the concepts on his own, which really speak to the power of discovery learning. But if you research and do a little bit of Googling on M.C. Escher, you'll see some of his really cool tessellation artwork. And in addition, some of the other math mystery artwork that he did, and it's fascinating to see how he could make illusions using different mathematical principles. But you can allow students to explore and make their own tessellations using the Illuminations Tessellation Center. It's a fun tool to explore. So if you want to pause this and try that interactive activity, feel free to do so. Letting students explore with transformation, symmetry, and location can be extended to several different activities, even further beyond tessellations, and your textbook contains several great activities. One of them is the pentomino position activity, which is activity 20.23. To do this, you'll have to have your students cut out 12 pentominos, and there's a handout when you click on the pentomino link, and you can make several copies and have the students basically cut out 12 different sets of 60 of these 5 little red squares, and give them a 2-centimeter grid paper and ask them to create 12 different original shapes, and then ask them to record how many of these shapes or how many different positions each of these shapes have. Now, what would qualify as different? Something would be different if when you rotate it or reflect it, it looks different than it did originally. So for instance, the cross shape will only have one position, because regardless if you rotate it 90 degrees, 180 degrees, 360 degrees, it's the same shape, and if you reflect it, it's the same shape. But 5 pentominos, either arranged horizontally or vertically, have 2 positions, because a rotation will result in it changing from vertical to horizontal or horizontal to vertical. But depending on the way that they rearrange their initial 5 pentominos, some of them can have as many as 8 different positions. This is a fun investigative activity for students to do, and it really helps them to come up with and develop the concept on their own for what differentiates different, and they get some real hands-on familiarity with rotation and rotation differences between 90 and 45 and 180. I shouldn't say 45, because they're going to be going, since this is on a grid paper, going 90, 180, 360. But it does give them that experience with making rotations with their own constructed figures so that they can feel more confident with doing so. This is a great activity that explores reflection, particularly with ordered pairs in the coordinate system. I remember doing activities like this in, I believe it was in high school, and they were really foundational for me in seeing how reflections create either similarities or differences between the original order pairs and your new order pairs, and it all depends on what axis you're reflecting on. So what I would like you to do, pause this and let yourself explore by starting out with an original creation, a figure A, B, C, D, E, and then make the reflections that they ask you to make and compare your new order pairs to the original. It's just good to have these experiences over and over again to refresh your memory about what will be the same and what will change. And that concludes the PowerPoint on geometry. I'm looking forward to our class on Tuesday because I think you're going to get a lot of great hands-on experience with potential activities you can use in your classroom to help further your students' geometric understanding.